Autocorrelation. One of the assumptions of CLRM states that the covariance and correlation between different disturbances are all zero. This assumption states that the disturbance UT and US are independently distributed, which is called serial independence. So if this assumption is no longer valid, then the disturbances are not pairwise independent, but pairwise autocorrelated or serially correlated. And this means that an error occurring at period t may be carried over to the next period t plus 1. And autocorrelation most likely to occur in time series data. In terms of notation, when there is no autocorrelation or serial correlation between the disturbances, we can write it as expected value of ui uj equals to 0, where I is not equals to j. And when there is a dependence between the disturbances, we say we have autocorrelation, and the way we write it is expected value of ui uj is not equals to 0. So example for time series data. So when we have autocorrelation, meaning that if there is a strike in this quarter, it will affect the output of next quarter. And for cross-section data, example, if there is an increase in consumption expenditure of one family, then the other family will also increase its consumption expenditure. So example, if you have an individual who is making renovation to the house, increasing their consumption expenditure, then the neighbor of that family will also make a renovation to the house. So this is how you see that there exists autocorrelation in cross-sectional data. So usually autocorrelation happens in time series data. So when you know that the strike, the effect of strike on output will be shown in the error term. So when the disturbance or the strike in this time period affect the output of next period, then meaning that the error term is correlated, or disturbance term correlated. So for two variable regression model, y regress on x, and we have the parameter beta 1 plus beta 2, and also we have the disturbance or error term. So when we say that the disturbance, the error term in one period will affect the error term in the next period, or previous error term is correlated with the error term in the existing period, then we can write the relationship ut equals to rho ut minus 1 plus epsilon t, whereby rho is between minus 1 and 1. So this is the error term example in t equals to 1, suppose 1980, and then this is the error term in 1979 example. So there is correlated between ut and ut minus 1, and the coefficient here we use rho. So this rho we call it as the coefficient of autocovariance, and the epsilon t here is the white noise term. So meaning in terms of the error term in this model, the expected value is equals to 0. So this relationship ut equals to rho ut minus 1 plus epsilon t, we call it as the Markov first order autoregressive scheme, or we say it as first order autoregressive scheme, or we say it as AR1, autoregressive order 1. So first order. So when we have this ut equals to rho ut minus 1, it is AR1. So if you have AR2, then it will be rho 1 ut minus 1 plus rho 2 ut minus 2, and so on. So why do we call it as autoregressive? So a model is called autoregressive is if the lag of the dependent variable is in the independent variable. So here a dependent variable is ut and the lag of it is ut minus 1, and this ut minus 1 is the independent variables in the model. So here we see it as an autoregressive model. So what are the consequences of autocorrelation? So when you have autocorrelation, the OLS estimators are still linear and unbiased, but the estimators are no longer having a minimum variance. So meaning that the estimators are not efficient, and therefore they are not blue estimators. And as a result, the usual T and F may not be valid. For model Y on xt, yt on xt, we have equals to beta 1 plus beta 2 plus ut, and this is the formula for beta 2 hat. And then the variance for this estimator is sigma squared over summation of xi squared. But when you have AR1 scheme, autoregressive one scheme, meaning that we are using ut equals to rho ut minus 1 plus epsilon t, and we want to show how we embed the AR1 scheme into the formula for variance of beta 2 hat. So variance of beta 2 hat when we're having AR1 is going to be this long formula, and we have this value rho that we need to substitute. When there is no autocorrelation, meaning our rho here is going to be equals to 0. So all this term will disappear, and meaning that the variance of beta 2 hat is going to be equals to the previous formula for variance beta 2 hat. But suppose rho is a positive number, which is larger than between 0 and 1. So meaning that the variance of beta 2 hat, when you have autoregressive 1, it will be larger than a variance beta 2 hat when you do not have any autocorrelation problem. So variance of beta 2 hat when you have AR1 is going to be larger than variance of beta 2 hat, and this is the case for rho is positive, and therefore we see that the usual OLS variance underestimates its variance under AR1, and therefore our T is no longer reliable. So it's example, we look into the formula of T equals to beta 2 hat over standard error of beta 2 hat for the zero null hypothesis, then we will overestimate the T value, and therefore will affect the result and the decision whether to reject or do not reject the H null. So this is a hypothetical example of a positively autocorrelated error term. So meaning that you have the AR1 scheme ut equals to 0.7 ut minus 1 plus epsilon t, whereby this epsilon t is the y error term and it's random. So you have this ut, the existing error term, and you have this ut minus 1, the previous error term, and you have suppose the rho is going to be equals to 0.7. So this is the u1 until u10, and assume that u0 is going to equals to 5. So for the error term in u1, it suppose it is 3.964. So if you look at the model, 0.7 times the previous error plus the epsilon t. So all this epsilon t is random, but this is the row 0.7, and this is the error term in the previous year. So again, if you look at U3, so U3 is going to be 0.7, 0.7, UT minus 1. So UT minus 1 will be 4.8010. So this is just a rounding error. And then plus an error term here, which is using 2.455, and then we get 5.8157. And again, the error term in U4 is 3.7480, and we can come out an equation of 0.7 times the previous error term plus another epsilon t, which is just random. So this is an example of hypothetical example. So this is purposely we construct the error term to able you to understand how does one error term is being affected by the previous error term. Okay, so meaning that when we have the AR1 scheme, UT equals to rho UT minus 1 plus epsilon T. So meaning that if rho is not equals to 0, and then we know that there will be autocorrelated between the error term.